Welcome to Cloud Wizard. In this video, we're doing a complete deep dive into distributed locks, the mechanism that lets multiple nodes coordinate exclusive access to a shared resource without stepping on each other. We'll cover how payment processors prevent double charges, how inventory systems avoid overselling, and how job schedulers guarantee exactly once execution across hundreds of servers. Whether you're preparing for a senior engineering interview or building distributed infrastructure at scale, this one is for you. Let's get into it. Welcome to Cloud Wizard. In this video, we are doing a complete deep dive into distributed locks, the mechanism that lets multiple nodes in a distributed system coordinate access to a shared resource without stepping on each other. If you have ever wondered how payment processors prevent double charges, how inventory systems avoid overselling the last item in stock, or how job schedulers ensure only one worker runs a cron task at a time across 100 servers, this video is for you. We will walk through the functional requirements, non-functional requirements, system architecture, end-to-end user journey, core models, low-level design, and the trade-offs that come up in every senior system design interview that touches coordination, concurrency, or consistency. Whether you are preparing for a FANG interview or building distributed infrastructure, let's get into it. Here is the core problem. In a single process system, you can protect a critical section with a mutex or a semaphore and everything works correctly. But in a distributed system, you have tens, hundreds, or thousands of processes running on separate machines, all trying to operate on the same shared resource, a database row, a file, an inventory count, a scheduled job, or a payment record. There is no shared memory. There is no single lock object. Network partitions happen. Processes crash mid-operation. Clocks drift. If two nodes both believe they hold the lock at the same time, you get double charges, corrupted data, or duplicate work. The naive solution of using a database row as a lock breaks down under high load and does not handle process crashes cleanly. You need a purpose-built distributed locking mechanism that is safe, live, and fault-tolerant, even when nodes fail or the network splits. Let's walk through the functional requirements. First, the system must provide a lock acquisition API that a client can call to attempt to exclusively hold a named lock, with a configurable timeout for how long to wait if the lock is held by someone else. Second, it must provide a lock release API, so the holder can explicitly free the lock when the critical section is done. Third, the lock must have a time to live, also called an expiry or lease, so that if the holder crashes before releasing, the lock is automatically freed after a bounded time, and the system does not deadlock forever. Fourth, the system must support lock renewal, also called heartbeating or lease extension, so a healthy long-running holder can extend the lease without dropping and reacquiring the lock. Fifth, the system must enforce ownership, meaning only the process that acquired the lock can release it, preventing a slow or late process from accidentally releasing a lock it no longer holds. These 5 capabilities are the minimum viable distributed lock. Now the non-functional requirements. Safety is the most critical. At most one lock holder at any moment, even under network partitions and node failures. This is the mutual exclusion guarantee. Liveness is the second. The system must eventually grant the lock to a waiting client as long as a majority of nodes are healthy. No indefinite starvation. Fault tolerance is the third. The system must survive the failure of individual lock servers without losing safety. Latency matters too. Lock acquisition and release should complete in single-digit milliseconds in the happy path. Durability is nuanced. Locks are ephemeral by nature, but metadata like lock ownership and expiry must survive a single node restart without corruption. Scalability is the final axis. The system must support thousands of concurrent lock namespaces without bottlenecking on a single coordinator. These requirements create real tension. Stronger safety often means higher latency, and you must be ready to discuss that trade-off explicitly. Here is the high-level system architecture. On the client side, applications call a distributed lock client library, which is responsible for generating unique tokens, managing TTLs, sending heartbeats, and handling retry logic transparently. The client library communicates with a lock service tier. There are 2 dominant implementations at this level. The first is Redis-based, using a single Redis primary with a Lua script for atomic compare and set, or the Redlock algorithm across 5 independent Redis nodes for higher fault tolerance. The second is consensus-based, using ZooKeeper or ECT, which run the Paxos or Raft consensus protocol internally and offer stronger guarantees. Above the lock service, a monitoring and observability layer tracks lock acquisition rates, contention, TTL expirations, and lease renewals. An admin dashboard surfaces lock health and allows operators to inspect or force release stuck locks in emergency situations. The key metrics to know: cold lock acquisition latency at the 99th percentile. This tells you if the lock service is a bottleneck under contention. Lock acquisition success rate, the fraction of attempts that succeed within the requested timeout, which reveals how much contention exists for hot namespaces. Lock TTL expiration rate, how often locks expire without being explicitly released, which is a signal of crashing clients or network issues. Lease renewal failure rate, how often heartbeats miss, which can cause a healthy holder to lose its lock. Lock contention ratio, the ratio of queued waiters to active holders per namespace, useful for capacity planning. False release rate, how often a process releases a lock it does not actually own, which indicates a fencing token or ownership bug. And end-to-end critical section duration, the actual time clients hold the lock, which drives TTL configuration. Let's trace the end-to-end user journey. A payment service processes a high-value transaction for user account 1234. Before debiting the account, the payment worker calls the lock client library with lock name account, lock 1234, and a TTL of 5 seconds. The library generates a unique token, for example a UUID, and issues a set NX PX command to Redis, which atomically sets the key only if it does not already exist. Redis returns success. The worker holds the lock. While processing, the worker sends a heartbeat every 2 seconds to extend the TTL. Processing completes in 3 seconds. The worker calls release, and the client library executes a Lua script that checks the stored token matches before deleting the key, ensuring ownership. A competing worker that tried to acquire the same lock during those 3 seconds was told to retry, waited, and now successfully acquires the lock for its own operation. No double debit occurred. The core models and algorithms. The single-node Redis lock uses set key value NX PX milliseconds, where NX means only set if not exists and PX sets the expiry in milliseconds. The value is a unique token per client. Release is a Lua script that reads the value, compares it to the caller's token, and only then deletes, making check and delete atomic. Redlock extends this to 5 independent Redis nodes. The client attempts acquisition on all 5, measures elapsed time, and considers itself the holder only if it succeeded on at least 3 nodes and the elapsed time is less than the TTL minus a safety margin. ZooKeeper uses ephemeral sequential nodes under a parent path. The client creates a znode, checks if it has the lowest sequence number. If yes, it holds the lock. If not, it watches the next lowest node and waits for a deletion event. The key trade-off. Redis Redlock has lower latency but weaker safety guarantees under clock skew. ZooKeeper has stronger safety but higher latency and operational complexity. Now the low-level design deep dive. The lock record schema in Redis contains the lock key as the namespace name, the value as a UUID plus process ID to ensure global uniqueness, and the expiry in milliseconds. The acquisition path uses a single atomic Redis command, set key token NXPX TTL, which avoids any race between checking existence and setting the value. The release path executes a server-side Lua script. If redis.call, get, keys 1, equals arg1 then redis.call, del, keys 1, and return 1, else return 0. This is critical. Without this atomic check and delete, a slow process that had its lock expired could accidentally delete a lock now held by another process. The heartbeat service runs in a background routine or thread inside the client library, calling pexpire key new TTL, every TTL divided by 3 milliseconds. If the heartbeat fails 3 times consecutively, the client library assumes the lock is lost and signals the application to abort the critical section. The fencing token is an additional monotonically increasing integer that resource servers can use to reject stale requests from a process that lost its lock, but has not realized it yet. Key takeaways for your interview. First, always lead with the safety versus liveness trade-off. No distributed lock algorithm can simultaneously guarantee both in the presence of arbitrary network partitions. Be explicit about which you prioritize and why. Second, the difference between single-node Redis locks and Redlock is about fault tolerance under node failure, not about throughput. Single node is simpler and faster but creates a single point of failure. Third, ZooKeeper and ECK provide stronger consistency guarantees via Paxos and Raft, but add operational complexity and higher median latency. Use them when you need leader election or watch semantics in addition to locking. Fourth, fencing tokens are the correct answer to the problem of a process that holds a stale lock after a long GC pause or network partition. The resource server validates the monotonically increasing token and rejects out-of-order requests. Fifth, TTL configuration is a critical design decision. Too short and healthy holders lose the lock. Too long and crashed holders block the system. If you can articulate these 5 points with concrete trade-offs, you will signal strong senior-level distributed systems thinking. That's it for distributed locks. If this helped you, like and subscribe, and I'll see you in the next one at Cloud Wizard. And that's a wrap on distributed locks. We covered the full picture from the core mutual exclusion problem through Redis SET NX, Redlock quorum, ZooKeeper ephemerals nodes, fencing tokens, lease renewal, and the low-level design of the Lua compare and delete release script. If this video helped you, please hit that subscribe button and the bell icon so you never miss a new system design video. Drop your questions in the comments below. I read every single one. See you in the next one at Cloud Wizard.